This video is for Math 0242-1342. We're starting Chapter 7 here, and the first assignment has 3 sections, 7.1, 7.2, 7.3. This is a concept called the normal distribution. It's a symmetrical graph that's bell-shaped, and it technically goes from negative infinity to infinity. But most of it happens within the first 3 standard deviations. You might remember the empirical rule of Chapter 3, where we would go 1, 2, and 3, and -1, -2, and -3, and they would have you memorize that 68% of the area happens within the first standard deviation either way. 68%, and then 95% happens in the first 2 places. And if you go from -3 all the way to 3, that's 99.7. Well, back in Chapter 3, they would also have to tell you that the graph was bell-shaped in order for this to work. So now we're going to study this a little closer. Back there, all we could do was go between -1 and 1, or -2 and 2, or -3 and 3. We couldn't even do like -1 to +2 back then. Now, not only can we do that, we can even go in between. We can go from -1.17 to +2.63 if we wanted to. So here it says, find each of the shaded areas under the standard normal curve, round to 4 decimal places. Okay, the good news about most of this chapter is you're doing 2 things for pretty much for the whole chapter. When the problem says find area, or synonymously probability, find area or probability, there's a function in the calculator called normal CDF, somewhat similar to binomial CDF and Poisson CDF, except those are discrete cases and this is a continuous case. Or the other half of the chapter is find a score or value. And then we do, it's literally the opposite case. Opposite, sometimes it's called an inverse. This is called inverse norm. And in both, since they are opposite cases of each other, the part that's given to you that lets you do the problem is the other kind of problem. So either they give you the score or value and you're trying to find area or probability, or they give you the area or probability and you're trying to find the score or the value. So you don't want to focus in on, oh, I see the word area in there, it must be this. It's not about just finding one word, it's what are they asking you to find? This says find each area. The area is blank, I'm looking for area. So focus in on what is it asking you to find. This one's asking me to find area, so that's a normal CDF. Each of normal CDF and inverse norm, they each have 3 cases to do. The best case of a normal CDF is when you go between 2 values. Or you can go less than or to the left. Those are sort of synonymous. Greater than or to the right. We have on this very first homework problem, it's got an area shaded to the left of a z-score. So this -192, that's a z-score, and like it was in Chapter 3, except there we could only do it if it was exactly -1, exactly -2, or exactly -3. So here we're basically going from -1.92 all the way down to -infinity. So the best case of a normal CDF is when you go between, and when you get that case, you put the smaller number first, and then the bigger number goes second, And then the mean and standard deviation are third and fourth. And really, that's what you do on every problem. It's just that when they ask you to go between two numbers, they give you both of the numbers you need. When it's to the left or to the right, greater than or less than, then they only give you one number. But the other number is either negative infinity or positive infinity. So really, going to the left is the same thing as saying go between negative infinity and negative 1.92. I can't do, the calculator doesn't have an infinity button, so I can't do negative infinity first. So the way we trick our calculator is, instead of negative infinity, you're going to put negative 999. That usually is big enough to act like an infinity. And then whatever's given goes second. And then the mean and standard deviation are third and fourth again. If it's to the right, you're going to be starting at a z-score that they give you, and you'll go to the right forever to infinity. So then we put the given number first, and then whatever we use positive 999 to act like a positive infinity. So two more things is that in the very first section of the normal chapter, in this case chapter 7, in 7.1, everything's what's called a standard normal. It even said that here, under the standard normal curve. The standard normal curve is the one we dealt with in chapter 3, where the mean is considered to be 0 and the standard deviation is 1. And that's why when you draw these graphs in chapter 3, we always put 0 in the middle, and then we went 1, 2, 3, and -1, -2, -3. But once we get to section 7.2 and beyond, then we're not going to be limited to that. Then the mean and standard deviation can be whatever we want them to be or whatever they tell us. So good news is that any problem that's coming from 7.1, it'll either say under the standard normal, or if they talk about z-scores, that's automatically a standard normal. And when it's a standard normal, then you automatically get to put 0 in this third slot and 1 in the last slot. But as soon as we get past 7.1, then we'll put other numbers there besides 0 and 1. Also, we have this difference between what I call the typers and the pasters, and this calculator I use is an older one. So I'm what is considered a typer. So I have to press second vars. We all would hit that. And if you remember how you up arrow to get to the binomial and the Poisson stuff, here you don't want to up arrow. It's the second one from the top. Normal CDF is 2 and inverse norm is 3. So I'm going down to number 2, normal CDF. When I press enter, it takes me back to the main screen. Let's see if I can move this so you can see it better. I'm on the main screen now, and it says normal CDF with a parenthesis. So this is why I call these typing calculators, is I have to type these 4 numbers in, and I have to know the order they go in and put a comma between each one. And watch out, there's a difference between the negative button down here at the bottom right next to the enter. This is the negative. It's different than the subtraction button. So I want to type negative, not the subtraction button, negative 999, comma. So I'm starting out here on the left at negative 999, and I'm coming up to this negative 1.92. Negative 1.92, comma 0, comma 1, because they said it was a standard normal. And this is what typers have to do, and some of you may be a typer. I get students even in my in-person classes that when they hit normal CDF or binomial PDF or whatever, it takes them back to the main screen, and there's just a parenthesis way, and you have to type everything. If you are what I call a paster, what happens when you go to normal CDF and press enter, it takes you to a separate screen. And it has normal CDF at the top. And then what happens is it says lower bound or lower. And that means the smaller number. So you would type negative 999 in that slot. And it won't even let you put a comma, so don't try putting a comma. So don't put a comma, then down arrow to where it says upper, and then you would put negative 1.92 there. And I think the first time you go into there, if you've never used that calculator before, it'll already have the 0 and the 1 in the third and fourth slots. That's what it defaults to. Or as soon as you change them away from 0 and 1, you can always go back and put them as 0 and 1 as needed. And then right below the 0 and the 1, there's the word paste. That's why I call them pasting calculators. And you go down and press paste. As soon as you press enter on paste, it'll take you back to the main screen and you'll have exactly what I have now. So the pasting screen is just more user-friendly. It reminds you of the order. Lower number first, upper number second. The mean goes third and the standard deviation goes fourth. And when you press paste, it puts all the commas in there for you as well. So it's just a little more user-friendly is the only difference. But it's all the newer calculators. If you bought your calculator in the last 4 or 5 years, they all have this feature where the older ones don't have this. It was a nice upgrade that they made to the calculators in recent years, but so I always have to explain it both ways because I get, in-person class, I'll get maybe 2/3 have the newer calculators now and maybe still 1/3 they've had their calculator for years, maybe back when they were in high school, or it was a hand-me-down and the brothers and sisters used it for a while and now this person has it. Or maybe you just bought it from somebody used and it was really old. So I still get people that have the older version besides me using this one right here. So press enter and you get the answer here, 0274. 0274. Oh, they want me to answer all 4 parts before I check any of them. So this is a case where you go to the left, and the next one might be to the right. Yep, see, to the right. So the only difference here is I'm going to do 1.03 as the lower number, and positive infinity will be the upper number. So I'm going from 1.03 up to infinity. Second vars, normal CDF. 1.03 goes first. 999 goes second. 0's third, and 1 is last. Whether you're a typer or a paster, that's the order you put them in. And the answer is 1515. And then they're probably going to have a between case. Yep, see, between 2 numbers. And it doesn't even matter if the 2 numbers are both negative, both positive, one of each. It doesn't matter. We couldn't do this in chapter 3. It doesn't matter that I'm going from negative 176 to negative 65. That we couldn't do this in chapter 3. We don't even care what numbers they give us here in chapter 7, though. So second vars. Now, one thing I forgot to mention is there's a normal PDF and a normal CDF before you get to inverse norm below that. And we never use normal PDF in statistics, actually. So remember how there was binomial PDF and binomial CDF, Poisson PDF, Poisson CDF. So this doesn't have that. I mean, this chapter doesn't have that because PDF is when you're at exactly one spot. And normal curves are continuous. So you can't get the area or probability at one spot because even in geometry, the area at one point is nothing. Area, you have to move from one point to another to have area. And so then you may be wondering, well, why is it in the calculator then if we never use it? Normal PDF, what it would actually do if you use that, you would just put one number in instead of 2 numbers, and it would tell you the height of the curve at that given spot. In statistics, we never need to know how tall the curve is. But in other math classes, calculus, actually there's a lot of calculus formulas that we use in statistics, and we don't have to understand any calculus to use them. But calculus uses this stuff too. They even do normal curves. And sometimes in calculus, they actually need to know how tall a curve is at a certain spot. So I guess the calculator company programmed that to help them out if they need that. But luckily, we just never use that one. So it's good news for you. It's less stuff to know. You always do normal CDF, never normal PDF. It's always normal CDF, and then this one's always inverse normal when we get to the opposite case. So between's the best case because you put the smaller number first, the bigger number second. You don't need to worry about any infinity or negative infinities. So the smaller number is the one on the left, the bigger number is on the right. So I need to put negative 176 first. Second vars, normal CDF, the second option from the top. Negative 1.76 is a smaller number, comma, negative 0.65 is the bigger number, 0 and 1. 2186. Okay, here's kind of there's really three main cases. This is technically a fourth case, but I don't consider it to be a fourth case because there's a way to do it that uses one of the first three cases. There's two options you can do here. The shaded area to the left, that was part 1 of 4. And then the shaded area to the right was part 2 of 4. So you could repeat what you did to get these first two answers. Remember this one to the left and this one to the right. So you could do a normal CDF going to the left where you start at negative 999 and go all the way up to this negative 0.26. Get that answer and write it down. Then you could do another normal CDF where you go from 1.98 all the way to 999 and write that one down and add the two answers together. Just like in geometry, if you have like a triangle sitting on top of a square, kind of like you're painting the front of a house where there's a garage that's rectangular, but then the roof above it's triangular. So if you want to get how much paint do I need on a front of a garage and a roof, you find the area of the rectangle and you find the area of the triangle and you add the two areas together. So you can find the left area, you can find the right area and add them together if you want. But that takes 3 steps. Or you can do this all in one step if you treat this as the opposite of part 3. Normal CDF is built to find area between. And this one you want the area between, so you just go straight to a normal CDF and go between these two numbers. Well, this wants everything except for what's in between. But what if I find the area that's in between? What if I do what I did on part 3 and go normal CDF? Smaller number is negative 0.26. Bigger number is 1.98. And of course, 0 and 1 are always going to happen for now. So I got an area between negative 0.26 and positive 198, but I don't want that for the answer. That's the wrong answer. But it's not like a random wrong answer. It's the opposite wrong answer. I want everything except for that. And that's that idea, that complement idea again about the rain and the no rain. If there's a 60% chance of rain, 60% chance of rain, what's the chance it doesn't rain? 1 minus. If you do 1 minus this answer you just got, then you'll get the answer in 2 steps instead of 3. So this is the method I like better, is I treat it like it's a between case and go in between the two numbers, even though we want everything except for that. And then if you 1 minus that answer, you get the correct answer. 3974. Or you just find each one separately, like part 1 and part 2, and add them together is another way to do this. Okay, so that one. Okay, sometimes these are off slightly because of the technology. I'm using technology to do this, but they think you should be using a table in the back of the book to do these. Usually they agree, and notice the first 3 answers were correct. So what's happening is I'm getting a more accurate answer, and theirs is slightly off because they're using tables. So if I were to do these areas separately, there can be some rounding on each one is what's causing this to happen. So what if I go from negative 999 to negative 0.26 with 0 and 1? That's the left side. Whoops, okay. That's weird that it's... So maybe I did type something wrong up there. Let me try that other one again. Normal CDF, was it negative 0.26 or did I type it wrong? Negative 0.26. Negative 0.26 to 1.98 was 0 and 1. Yeah, I must have typed that wrong earlier because I got the same answer this time doing a different method. So, okay, so let's try this. Let's 1 minus this answer. 42112, but there's an 8 after that, so make it 4213. I had some kind of slight typo, obviously, because it's off significantly. It's not just a little bit off. 4213. There, see, now it's correct. Okay, so yeah, I just typed something wrong. In fact, I can go back and see what I typed. If I hit second enter a bunch of times, it'll call up what I typed earlier. Oh, see what I typed? I had 198. It didn't get the point in there. Sometimes I click a button and it just doesn't register on this. This calculator is very sensitive. So I had negative 0.26, but then I had 198 instead of 1.98. So there was a typo on my part is why that was wrong. Okay. So again, notice I'm looking for this right away. Find the area. Find area. That's normal CDF. And this one wants to the left. Anytime it's to the left, see if I can do this where you can see them both at the same time. To the, whoops, no, that's not what I wanted. Okay, maybe it won't let me do that. Okay, to the left, you do normal CDF. Well, you're doing normal CDF anyway because it's find the area. Whoops, let me clear all this. Normal CDF, second one down. To the left, you always put negative 999 first. You're going all the way to the left to negative infinity. And then you put whatever given number is here, 2.36. It does say under the standard normal again, standard normal. So 0 and 1 for third and fourth slots. Whoops, yeah, I hit the comma, but it didn't register. There. 9908, but there's a 6 after that, so 9909. That's the first case of the other problem too. And now they want me to go to the left again of a negative number. It doesn't even matter if the first number is positive or negative, or the one that's given to you, I mean. Both of these are to the left, so I'm doing normal CDF, and negative 999 is first on both of these. They're doing 2 of that left or less than case. I guess they're just saying the z-score can be positive or negative. This time the z-score is negative 2.13, 0 and 1. But these two parts are not really different for those of us using the graphing calculator for this. 0165, but there's an 8 after that, so make it 0166. Find the area, same thing. Find the area under the standard normal. Now it wants me to go to the right of 1.19. That's the second case, the second part of the first problem. This is when you do normal CDF and you put the given number first, then positive 999 goes second, 0 and 1 is third and fourth anytime it's standard normal. 1170, there's a 2 after that, so keep it 1170. Okay, see, to the right again of a negative number. This actually is done differently if you're using the tables, the old-fashioned way of doing it, but if you're using technology, these two parts are not really different to me. I'm doing normal CDF in both of them. I'm putting the given number first. And then 999 goes second, and then 0 and 1. 98537, so bump that 3 up to a 4, 9854. They're trying to show the difference between a positive and a negative, but there is really no difference when you do it in the calculator. You don't really care what number they give you if there's just one given. And then here's one where two numbers are given to me and I'm trying to go between. Still says find the area under the standard normal. Between two, whenever you're going between two, you put the smaller number first. The lower bound, they call that. The lower one goes first, 1.36. The upper goes second, 1.78. It's still a standard normal, so still 0 and 1 at the end. So you're basically just doing these same three cases over and over again. Either it's to the left, it's to the right, or it's in between. 0493, but bump that up to a 4 because of the 7. 0494. And here's a between where one of them's negative and one of them's positive. That doesn't bother me. I always put the lower number first, and negatives are smaller than positives. So the negative is definitely the lower one. Normal CDF, negative 0.42. And positive 2.47 is definitely the upper number. Still standard normal, so still 0 and 1. 6560. So problems 2, 3, 4, they're just going through the three cases kind of individually where they think there's a difference between giving you positive and negative numbers, but there really isn't. Okay, now we're doing the opposite problem because now it does not say find the area or find the probability. Now it says find the z-score. And they're giving me the area. This is exactly backwards. The first four problems, they give you a z-score and you got to find the area. Now they give you an area and you got to find the z-score. That's the other half of this chapter. See? Find a score or a value, that's when you use inverse norm. Now, inverse norm has three cases too. The best case of normal CDF is between because you just put the two numbers in that they give you. Whenever it's less than or greater than, you got to figure out, is this where I put 999 second or negative 999 first? The best case of inverse norm is to the left or less than, because then you just put in the given area. If it's to the right, you have to do 1 minus the given area. That's the value you'll actually use. And if it's in the between or the middle portion of the graph, you have to do 1 minus the given area and divide by 2. Unless there's now another weird thing happened is first people started showing up to class with these pasting calculators. And then there's been an upgrade of the upgrade, actually, kind of like a 2.2 version. Now I'm getting some students who not only have pasting screens, but when they go to inverse norm, there's another added feature that's very useful if you have it. When you go to inverse norm, you'll know if you're a paster or a typer right away because you'll either be on the main screen or back in a separate screen. But some pasters have this and some don't, in my in-person classes anyway. Some pasting screens at the bottom, before it says paste, there's an option to pick left, center, and right. Or maybe it says left, middle, and right, but it's either center or middle. Left, center, and right. If you have that feature, it's extremely nice because then you don't care about this detail right here. So let me show you this problem and then I'll explain what that means. So they want me to find the z-score. That's inverse norm. You always have to know, are you doing normal CDF or inverse norm? The area is to the left, is 0.81. That's what we all like. That's the best case, the left one. anytime it's to the left, you don't have to make any adjustments. So I'm going to do inverse norm, which is second vars and the third one from the top. If the area is going to the left, then you just put it in as is, whether you're a typer, a paster, or even have the left, center, right options. So the given area is 0.81. And then okay, there's something weird on the screen here. Okay, 0.81 and then 0 and 1. It only needs 3 things. It's not like normal CDF that needs 4. All it needs is the area first and then the mean and the standard deviation, which are still 0 and 1 until we get past this section. Area to the left. That's what inverse norm is built to do. So I'm getting a area, the area was given to me. I'm getting a z-score of 8.7. Maybe they want 2 decimals. Sometimes they do 2 decimals for, here it doesn't say. Okay, so maybe I don't know if they'll take 2. Let me try that. 0.88. Usually what happens is that areas are 4 decimals and z-scores are 2, but let's see. Yeah, okay, that's fine. 0.88. So that's the best case, is when the area is going to the left, but probably the next problem is going to go to the right. Yep. Find the z-score for which the area to its right is 0.42. So if you have one of these pasting calculators, and when you go to inverse norm, if you see left, center, right at the bottom, go over to right and click that. And then you can just put this 0.42 in. You don't care which case they're giving you. All 3 cases are equal for you. The rest of us have to struggle through this a little. When it's to the right, you have to do 1 minus the right first. So I have to do 1 minus 0.42. If you have left, center, right, don't do this. But if you're a typer, you definitely need to do this. And if you're a paster, but you don't see that left, center, right at the bottom of the inverse norm, then you have to do this. And there's 42 to the right, and that means there's 58 to the left, because it's like rain and no rain. So anybody that doesn't have the left, center, right options has to go to inverse norm. And whether you're a typer or a paster, we have to put 0.58 in here with 0 and 1. If you are a paster that has that left, center, right, you should type 0.42 in, then 0 and 1, and then click right. As long as you click right, it'll do it correctly. And then I'm just going to make this 0.20 because they're apparently taking 2 decimals here. And then maybe we'll get the in-between one next. Let's see. Yeah, see the middle, 96%. So if you have the pasting calculator with the left, middle, right option, put 0.96 in and click middle. You don't care that this is a hard case for the rest of us. For the rest of us, we have to do 1 minus 0.96 and divide by 2. The rest of us, we always have to have area to the left. That's what inverse norm was built to do. It wasn't until these recent calculators that you can just, it doesn't matter if you're going to the left or not. But the rest of us need to go to the left. So 0.02, that's what I'm going to put into the inverse norm. Because if there's 96 in the middle, there's 2 on the left and 2 on the right, and that makes it add up to 100%. But if you have the ability to pick center or middle, don't put 0.02 in. Put the 0.96 and click center or middle, whatever it says, and then you won't have to worry about how did you get that 0.02. Negative, now here's an issue too. When there's 96% in the middle, where is it? Okay, here we can go. When you have 96% in the middle, you're actually getting 2 z-scores. And because these are standard normals that are centered at 0, the calculator spit out the left one for me, which was negative 2.05. Negative 2.05 is right here. Well, the graph is symmetrical, so if this is negative 2.05, this must be positive 2.05. So on these middle ones where there's like 96% in the middle, you're always going to get two answers, one positive and one negative. In fact, it should say find the z-score. See how it's plural now. Find the z-scores that bound this middle area. So, and they even have two answer blanks too. So the one where you're doing the center of the middle will have two answers, but they're always the same, positive and negative of each other. And if it's to the left or to the right, there'll only be one answer, and it actually could be positive or negative, but it'll just be one. So there's all three cases. And if you have the ability to pick left, center, or right, then all three of these problems are equally to you difficult-wise. To the rest of us, people find these get harder and harder. So left is what it's built to do. You just put in whatever they tell you. Right, you have to do 1 minus what they tell you. And if you don't do that, it'll be wrong. And between, or the middle, you have to do 1 minus what they give you and divide by 2 before you type that into the inverse norm, even if you're a paster. Unless you're a paster that has that left, center, right option at the bottom. So I don't know why I get people to show up in class and they're pasters, but they don't have it. And the only thing I can think of is it must be the year the calculator was made. So if yours was made like 2020 or 2021, then you probably have pasting features. But if yours was made like 2022 or 2023, that's about the years when people started showing up with these left, center, and right options. Because in my in-person classes, many students go buy a brand new calculator at Walmart or Target, and they have a brand new one. So that's every time this calculator company improves the calculator, then in the future students show up with the improvements. Okay, so we may be done with 7.1 now. Let's see. Yeah, see, I know we're done with 7.1 now because now the mean is 66 and the standard deviation is 15. So once they tell you that, then it's no longer a standard normal. Standard normal automatically means that the mean is 0 and the standard deviation is 1. And they might not tell you that because they think you're supposed to know when they say standard normal that that's the rule. But the moment they tell you the mean is something other than 0 and the standard deviation is something other than 1, then you immediately know you don't have a standard normal anymore. But the good news is everything else in 7.2 is identical to 7.1. There's no new rules to learn here. Everything's the same, except you just don't put 0 and 1 in those last two slots. And what you put in instead is literally what they have to tell you. So they have to tell you the mean and the standard deviation. So these problems are no harder than what you just learned. In fact, this will help reinforce what you have learned. Okay, it says what proportion, another word for proportion is probability. So this is kind of asking you, what is the probability that the proportion of the population is greater than 101? So find area or probability or proportion, all that's synonymous. So we're back to doing a normal CDF here. The big difference is we're not going to put 0 and 1 at the end. That's really the only difference. And they want me to do greater than 101. Greater than 101 is greater than or to the right. Then you put the given 101 first, 999, and then instead of 0 and 1, you put what they say they are. So this is that third case of a normal CDF right here. Now, one issue is once these numbers start getting larger, like 101 or 80, those aren't too large, but they want me to be greater than 101. So when I do second vars normal CDF, as soon as you put 101 here, what if that was 901 instead of 101? Well, then 999 may not be big enough to act like infinity. Usually it's good enough, especially in the standard normal section, 999 is plenty big enough. So kind of as a rule of thumb, whatever the size of the other number is, 101 has 3 digits in it. put one more 9 than that. I'm going to put a fourth 9 just to make it significantly bigger so that acts like infinity. And then 0 and 1. Oh, I'm sorry. See, not 0 and 1. Now I got to put in what they say they are. It's 66 and 15. That's the only difference. You have to put an extra 9. That's not that big a deal. But you don't put 0 and 1. You put 66 and 15. 0098. 0098. And then here's the case that's less than 80. Less than 80. So now that's the case where you put negative 999 first. Normal CDF, negative 999, and I can just leave 3 9s because the 80's only got 2 digits in it. But then instead of 0 and 1, you put the 66 and the 15. 824, bump the 6 up to a 7, 8247. There, see, that's the only difference. So 8's just like 1 through 7, except you don't put 0 and 1 at the end. That's really the only thing different about it. So here's a mean of 51. Sigma 6. What is the 81st percentile? So that's a realistic problem. If you take the SAT or the ACT, they'll tell you what percentile you were in the test takers. And the closer to 100 means the better you are. The 81st percentile means you're equal to or better than 81% of all the test takers on the SAT or ACT. So what is the 81st percentile means that 81% of the area is, or probability is below you. So we want to know what score you got. What's your score, basically? It doesn't say that here, but that's the interpretation of percentile, is what score is that. There's 81% of the area below, and it always is less than or equal to. Percentile automatically means less than or equal to. So this is the classic example of an inverse norm where it's already going to the left. An 81st percentile, put 0.81, change the percent to a decimal. But then instead of putting 0 and 1, I have to put 51 and 6 that are quoted here in the problem. 51 and 6. And then they might have this rounded to the whole number just because it's usually like for test scores. Whatever their percentile ranks are always about test scores or GPAs. But it does say round to 1 decimal place. So if they tell you where to round, definitely do that. 56.26, but bump that up to a 0.3. 56.3. Okay. In a recent study, the Centers for Disease Control reported that blood pressures of adult women were approximately normal with a mean of 80.1. So it's not 0. And the standard deviation is 9.9. What proportion, another word for proportion is probability. What is the probability that they have a blood pressure lower than 71? What is the probability? What is the proportion? That's back to the normal CDF. So it does take some practice to know, when am I doing normal CDF, when am I doing inverse norm? But for the most part, the whole chapter is one or the other. So you got like a 50-50 chance on any problem. And usually on tests, students either always know which one of the two it is, or they get it wrong every time, unfortunately. But find the area or find the probability, or proportions, another word for probability, that's normal CDF. Find some kind of score or value, that's inverse norm. And we're trying to do lower than, so that's left or less than. So we're going to put negative 999 first, then the given number, and then whatever they say the mean and standard deviation are. Lower than 71. So inverse norm, I'm sorry, I said it wrong, normal CDF, negative 999 to 71. And then the mean is 80.1. And the standard deviation is 9.9. Oops, I didn't get the comma there. Comma 9.9. 1789, but after the 9's another 9, so make it 1790. Think of 89, adding 1 to 89 and make it a 90. 1790. What proportion of women have blood pressures between? See, here's the between case. So now you don't need a 999. Now you put the smaller, lower number first, bigger number second, upper number, and then the mean and the standard deviation. So normal CDF between 72 and 92. Normal CDF, 72 is the lower bound, 92 is the upper. The mean's still 80.1, since I'm doing the same part. And the standard deviation is still 9.9. 6786, but there's a 9 after that, so make it 6787. And then here's the other case, greater than 90. So this is a good problem. It has all three cases. It's got the lower or less than case, the between, and now the greater than 90. Greater than 90 is normal CDF. 90 would go first. 999 is second, and then put the 80.1 and the 9.9 for the third time in a row. 1586, there's a 5 after that, so 1587. Is it unusual for a woman to have a blood pressure lower than 63? Okay, so that's, I thought maybe it was referring to one of the first three problems, but it's not. So we have to recalculate that one. That's like part 1 where it was lower than 71. So lower than 63 would be second VARS, normal CDF, negative 999 first, then 63, then 80.1, and then 9.9. Whoops, didn't get the point there. 9.9. 0421. Now, they don't want you to put that answer in. The question is it unusual? For us, the unusual cutoff is usually 5%. Anything lower than 5% is considered unusual. The 5% is a loose guideline for now. Later, it'll change between 1 and 10%. But if they don't mention it, then you assume 5% is considered unusual. And 0.04 is less than 0.05. This is unusual. It's unusual to get a blood pressure that low that maybe the doctors need to do something because maybe there's something physically wrong with the person. Whoops, I didn't fill all the boxes in. Oh yeah, here. It's unusual. I didn't think they wanted the answer, but they do. It's unusual because the probability is 0.04, whatever I had there, 0421. See, they want you to show that you're not just guessing that, yeah, I got an answer that's lower than 5%. That's when it's considered unusual. We're going to do this more in chapter 8, actually. 8 and 9, you'll see this more about something being unusual. They're kind of preluding it right now. Okay, so I think we're done with 7.2 now. So that's 10 problems down, 5 to go. So 7.2 wasn't a whole lot different than 7.1. Literally the only difference was you don't put 0 and 1 at the end. And then 7.3, another thing happens that makes this very similar too. So there's not really that much new here either. Two things before I do number 11. If, say you forget what the empirical rule of chapter 3 was. Turns out if you do normal CDF between -1 and +1, remember how we always had to have between -1 and +1, or between -2 and +2, or between -3 and +3. That's all we could do in chapter 3. And they said memorize those percentages. Now you don't need to memorize them, because if you do normal CDF and go back to where the mean is 0 and the standard deviation is 1, a standard normal, if you put -1 first and +1 second, remember it's 68, 95, 99.7. Here's the 68 right here. So you don't have to memorize that anymore. If you ever forget it, just do a normal CDF between -1 and 1. Or if I do a normal CDF between -2 and 2, this should have 0.95 for the first two decimals. See, 0.95. And if you do it between -3 and 3, it'll have 997 for the first three, because we're supposed to memorize those numbers in chapter 3. See, 997. So there's literally the empirical right there, 68, 95, 99.7. They didn't just make these numbers up off the top of their head to force students to memorize something. It actually comes from calculations. And you didn't know what the normal distribution was back in chapter 3, so they just kind of did the 3 basic cases there and said memorize them. But at least now when you take the final exam, you won't have to memorize those anymore. Okay, second thing is we need to do a new set of magic words. The first unit, we took a tour of Texas and went to different cities. The second unit had to do with sports teams here in Houston. So I thought of what I was going to do for the third unit. Okay, so you'll catch on to this theme probably pretty quickly. Let's do for the first magic word of Unit 3, which goes with sections 7.1, 7.2, 7.3. Send me the magic word of the planet Saturn. Saturn with the rings around it, Saturn. Saturn is the magic word for the first video of Unit 3. And then you can probably guess what the other 4, at least their topic will be, but you won't know which ones are coming next. Okay, so watch this right here. You mostly know how to do this right here. We want to find the probability. Find the probability, that's normal CDF, between two numbers. So that's when you put normal CDF. Smaller number goes first. 45.2. 50.6 goes second because that's the bigger number. And then the mean and standard deviation are not 0 and 1, but they have to tell me what they are. The mean is up here at the top, 48.5, and the standard deviation is 12.7. 48.5 and 12.7. Now, here's that's everything from section 7.2 all over again right there. Nothing to that is different than 7.2. The one thing that is different, though, is never in section 7.1 or 7.2, the first 10 problems, never in any of those problems did they mention anything about a sample size. But right here, there's a sample of 98 sessions that are examined. Once there's a sample size, then the following comes into play. If you go to your page 1 of the formula packet that I emailed you, you may have during the last test used the chapter 4 box and the chapter 5 box. Actually, the chapters here are off a little bit because this textbook does something else in chapter 4 and it pushes everything else back. So what's labeled chapter 4 here is actually chapter 5 in your book, and the one labeled chapter 5 is actually chapter 6. But here's what's normally a chapter 6. I'm used to these being chapter 6s, but now we're in chapter 7, the normal distribution. There's z-score formulas here. And then this is what's called the central limit theorem. The central limit theorem comes into play whenever there's sample sizes going on. 7.1 and 7.2 never had anything to do with sample sizes. But when there's a sample size, then the mean and the standard deviation that you put in at the end get affected slightly. In fact, the mean does not get affected, it just stays the same. This is saying that the mean, when there's samples involved, remember X bar is the symbol for mean, sample mean? So this is kind of like a mean of a bunch of averages. Get a bunch of people to go take a sample and report back to you what their averages are. If you average everybody's average, that's what this symbol means. And it turns out that if you do this in a normal situation, normal distribution, the mean of all your samples will equal the mean of the population. But the standard deviation that comes from all the samples doesn't equal just the standard deviation that's given to you in the problem. This is the extra step you have to do. The standard deviation only has to be divided by the square root of n, and it's really easy to not remember to do that because for the first 10 problems you never even worried about it. And it turns out that if you do this, if there's a sample of 1, if I divide by the square root of 1 at the very end, you get the same answer than if you don't do that. In fact, let me delete it first. See, if I do this the way we did this in 7.2, this is the answer, but it's going to be wrong here. If I hit second enter and tack on the square root of 1, it doesn't change. So that's the lesson, is I could have been doing square root of 1 all along since problem number 1. If the problem doesn't mention sample size, or if there happens to be a sample of 1, then it's the same as section 7.2, and you don't put anything at the end. But if the sample size is anything different than 1, then you have to tack this on at the end. So this had a sample of 98. I have to divide the sigma by the square root of 98, or this will be wrong. And notice the answer changed greatly. It went from 1.6 all the way to 94 just by doing that. 9441. Would it be unusual for the mean to be greater than? See, here comes this again, where we're going to say yes to that if we get a probability less than 0.05. See how it says the common cutoff is 0.05 at the end here. So would it be unusual to get a mean length greater than 51.5? So I'm going to do normal CDF again, greater than 51.5. So that would, you'd put that first, then you'd put 999, then put this 48.5, and then 12.7 divided by the square root of 98, because that's happening in this whole problem. And see, it is unusual because this is 0097. The probability I'm getting is 0097, which is less than this considered low 0.05 cutoff value. So yes, it would be unusual to get that because the probability is so low. When the probability is low, and what's considered low enough for us is less than 5%, when a probability is less than 5% or very low, then you don't expect it to happen. So if here comes a patient sitting in your doctor's office who has this situation, it's a very low probability of seeing a person like this, so that's unusual to have this kind of person here. Just like it's unusual to win the lottery, and winning the lottery has a very low probability. So that's the only thing different in section 7.3. is you just got to look at the formula sheet. Where do I have it? Here it is. Look at the formula sheet. It's easy to forget to do this, but in 7.3, anytime there's a sample size mentioned, you have to tack on this square root of n at the end. There was a case years ago, back in the 1800s and the early 1900s, there used to be a yearly World's Fair that would be placed in cities all around the world year after year. It was one of the biggest events of every year. There was a World's Fair in some major city every year. And in the 1800s actually, when the World's Fair was in Paris in the 1870s or 80s, Paris got the World's Fair one year around that time. They built the Eiffel Tower just for the World's Fair. That's why they have the Eiffel Tower in Paris. It was built for a World's Fair to welcome the world and look at what the French did for their engineering prowess. And the citizens at the time hated it. They said, what's this big ugly metal thing doing in the middle of our city? And then now it's like the most famous icon to go visit, and Paris has the most tourists every year of any city in the world. and everybody wants to get their picture by the Eiffel Tower, and it was actually hated when it was first built. That happened for a World's Fair, actually. At another World's Fair, there was a guy running a booth, and you know these booths, like even when you go to a carnival, like you throw a ball and you try to knock over bowling pins or toss a ping pong ball into a fish bowl, and if you're able to do whatever the little booth is about, you win a stuffed animal. There was a guy who had a booth like that, except at the World's Fair, except what he was doing was he filled a jar full of thousands of jelly beans, and he literally counted how many were in there. And then you paid the $1 or whatever it cost to play the game. And if you could guess the number of jelly beans within a certain range of it, like a certain percentage, like if you were within 5% of the real answer, you won the stuffed animal. And one day this guy decided, you know what, I'm going to write down every answer of every customer that comes here. And he got crazy answers. People would say, I guess maybe they were drunk or something at the carnival, but they would come in and pay the $1 and say 20, and it was clearly way more than 20. Why are you wasting $1 to do that? Or they would say 10 million, but it wasn't even close. But even with all the crazy low and the crazy high answers thrown in every so often, and then some people actually won stuffed animals too and got close to it. He went home one night and he took all the hundreds of answers he got that day, added them all up and divided by how many there were. That's literally what this symbol right here is. That's the mean of all the samples. And he was shocked to discover the answer was very, very close to the real answer. It was enough to win a stuffed animal, even with all the crazy answers included. It's a classic case of many heads are better than one. That's what the central limit theorem is all about. That when you pool a bunch of samples together and try to get the average and the standard deviation from that, the results turn out a lot better. In fact, look at the calculator. When I did it without the square root of 98, the answer was 0.1 something, and with the square root of 98, it improved the probability really high. We went from like a 17% chance all the way to a 94% chance by having a sample of 98 people working together, basically. See this sample of 98 here. That's what the central limit theorem is all about. So here it comes again. What is the probability? That's definitely normal CDF. But now they're talking about sample mean. So there's going to be some kind of sample size here. There's a sample of 80 households. And we want to be greater than 2. So find the probability. That's normal CDF. Greater than 2, you'd put 2 first and 999 second. The mean never changes, so when they say the mean for streaming devices is 2.24 in a household, that always stays the same. But then the standard deviation, whatever they quote you on that, 1.2, you have to divide that by the square root of 80. It's easy to forget to do that, but 1.2 divided by the square root of 80. That's the only thing different compared to the previous section. So 9632. What's the probability the sample mean is between 2.5 and 3? Same, all the information's the same except for that. Go between 2.5 and 3, so normal CDF, 2.5, 3, but the other part is the same as part 1. Put the 2.24 next, comma, and then 1.2 divided by the square root of 80. Zero, 2, 6, 3. Part 3 is probably going to be a less than because okay. Find the 20th percentile. So that they want the score, the value now. Now this is inverse norm. Find the 20th percentile. And luckily, percentile is always less than or equal to. And that's the best case of an inverse norm. So inverse norm 0.20. But you can do this even on inverse norm. Instead of putting 0 and 1, I'm going to put the 2.24. And the 1.2 divided by the square root of 80. That works here too, even if there's a sample of 80, I have to do this here. And then let's see where they want it rounded to. Round to 2 decimals. 2.12, but there's a 7 after that, so 2.13. Using a cutoff of 0.05, 5%, would it be unusual for a sample mean to be less than 2? Well, let's find the probability of being less than 2. Find the probability is normal CDF. Less than 2, you would put negative 999 first, then the 2, then the same last two values, 2.24, and 1.2 divided by the square root of 80. Is this going to be less than 0.05? If so, then it's unusual. It is less than 0.05. It's 0.368. 0.368 makes this unusual. It is unusual because the probability is low enough it's less than 0.05. So if you have less than 2 streaming devices in your house, you're an unusual household. Using a cutoff of 0.05, you think it'd be unusual to have fewer than 2 streaming devices? Explain. That's weird, isn't that the same question? Less than 2, fewer than 2. That's weird. Maybe it's like where the random generating of each part, that these don't have to be the same, but just the version I got, they were the same, because I don't see the difference here. So I'm just retyping what I had on part 4. I don't know why. No, okay, there is something different about it. Would it be unusual to sample mean less than 2? Oh, an individual. Oh, yeah, that's what's different. See how it says for an individual. See, this is what they're doing here is now they're trying to show you that it's not a sample of 80 anymore. That's what's different. An individual means a sample of 1, which is the same thing as not even putting that at all. You could delete the square root of 1. You can delete this divided by the square root of 1 if it's a sample of 1 or if they don't even mention a sample size. So see, the probability is a lot higher when it's a sample of 1. It's 4207. 4207 is not unusual, actually, because 4207 is not less than 0.05. This can commonly happen. If there's a 42% chance of rain and it actually rains, there's nothing surprising about that. It's not that you're expecting it to rain, but if it still rains, then you're like, okay, it was about a 50-50 chance of rain. So I missed this part about for an individual. So the first 4 parts here are all using this sample of 80. And then they threw this one in at the end to see what happens if it's just one person and not 80 people. That greatly affects the answer, actually. That's why you have to have that square root of 80 on the other parts. The mean annual income for people in a city is 41 in thousands of dollars, 41 with a standard deviation of 28. But a pollster draws a sample of 92 people. See, there's a sample size of 92. What is the probability? That's normal CDF. That the sample mean is less than 37. Normal CDF, less than 37 means you'll put negative 999 first, then 37. The mean is 41. The standard deviation is 28. But there's a square root divided by the square root of the sample size. Because it's larger than 1, it's 92. A sample of 92 people. So unless it's a sample of 1, like that last part of the previous problem, they said for an individual, or if you're back in section 7.2 and they don't even mention sample sizes there, then there's nothing to divide by. But anytime they mention a sample size larger than 1, then you have to do this. 0.853. What's the probability sample mean is between 38 and 45? So what is the probability? Normal CDF between 38 and 45. So put both of those in. No 999 this time. And everything else is the same. 41, 28 divided by square root of 92. Even if you're a paster, when you get to the fourth slot, you can literally type 28 divided by square root of 92 all in that same slot right there. You don't need to like calculate it first and then type it in. 7626. Find the 80th percentile. That's inverse norm. Inverse norm with a 0.80. And then you still put the 41 and the 28 divided by square root of 92. Four, 3, 4, 6, if they still want 2 decimals. 4, 3, 4, 6. No, they want 1 decimal. 4, 3, 4, 6. So I need to make that a 5 instead of a 4. Using a cutoff of 0.05, would it be unusual for a sample to be less than 32? So probability that you're less than 32, normal CDF, negative 999, 32, then the 41, and then 28 divided by the square root of 92, and we do have the square root of 92 here because they're still talking about the sample. And this has a very low probability, 0, 0, 1, 0. 0, 0, 1, 0, that's way less than 0.05, so yes, this is unusual. And then maybe part 5 is going to do the same thing as the other one and say for an individual. Yeah, see, for an individual. So that means the sample's only 1 for part 5. And if the sample's 1, you don't have to put it. So it seems like it's the same question, but that's really the only difference is get rid of this 92. Press second enter to call up the last statement, back up to the division sign, and just delete all of that. Take that completely out, because when there's a sample of 1, you don't have to put it. You can put it if you want to. If I hit second enter and tack on divided by the square root of 1, you can do that. But notice the answer is the same with or without the square root of 1. It's different without the square root of 20, what was it, 92, but it's the same with or without the square root of 1. So now it's not unusual because it's 3739. That's way bigger than 0.05. Now, since the probability is 3739, now it's not unusual anymore. Okay, 1 through 13 are finished. 2 left, 14 and 15. Okay. It turns out once you have samples going on, it's not that you automatically can do this. There's a couple of rules that come into play. If the population is known to be normal somehow, which basically would be one of two things, either they're going to tell you it is, or if you could get raw data and make a graph yourself like a histogram or a box plot, then you could see maybe it's symmetrical enough to be considered normal. But for us, basically, it's going to come down to whether they tell us or not. If I go back to 11, 12, and 13, I guess maybe does it say it here or not? I'm looking to see if they mention it here. No. Sometimes they mention this in the problem, but I guess because they were just teaching this at first, they're kind of ignoring that at this point. Yeah, it doesn't mention it here. But it can mention that in problems. I know it will in future sections. When you're reading these paragraph problems, they'll say, assume the population is normal. They'll add that to the paragraph sometimes. So if the population is normal, then any sample size is good enough for this to work. If the population is not normal, or if I don't even know if it's normal or not, then you need a sample size of at least 30. So a sample size of 32 is good enough that I don't care if the population is normal or not. Would it be appropriate to use it? Yes. Anytime the sample size is 30 or more, then you can definitely do this normal distribution work that we're doing. Okay, so if I go back to 14 real quick and try another one. Sample of 30, see, that's just barely good enough. Okay, maybe Some books say at least 30. Maybe this one's saying greater than 30. Maybe it has to physically be greater than 30. Let me try another one. 10. See, 10 is definitely no good. If it's under 30, definitely that's not good enough. Oh, no, wait a minute. See, it does say it. Drawn from a normal population. See, a sample of 10 would have been bad if they just didn't even mention if it was normal or not. But because it's normal, then any sample size works. But if they just said from a population with a sample of 10, then that would not have been good enough. Here's a sample of 14 drawn from a population. It doesn't say normal population. So that's not good enough. It's not at least 30. So apparently, I know some books say greater than or equal to 30. Apparently this one's saying you must be greater than 30. Because 32 worked, but 30 they said was wrong. So that's a little weird. I'm used to it being at least 30, but... Okay, but look for that. Either the sample size has to be greater than 30, then you click yes. Or if the sample size is 30 or less, then you got to see, did they say normal population? Then you can still say yes, but if they don't, then it's no. Okay, the probability distribution of X bar is called it's the sampling distribution because we're taking samples. The standard error, that's the name of this right here, this standard deviation formula. The one that has square root of n in the bottom, that it's called the standard error. It even says so here on the formula sheet, standard error. Standard error is the name of that standard deviation formula, but it's not the name of the probability distribution. But X bar is the symbol for sample mean, so this is sampling distribution. See, here it comes right now. The standard deviation of the sampling distribution is also called the standard error. The standard error of the mean. So just some technical terms. I know you probably wouldn't need to know that for a test, but 14 is a good problem actually, where the central limit theorem you can't just automatically do it. You either need a sample size greater than 30, or you have to know the population's normal. And here the sample size was 14, which is not greater than 30. And it just says it's from a population. It doesn't say normal population like the previous one did. So that's not good enough to do it. Then you can't just automatically calculate these. Whenever there's a sample size, you got to worry about this little rule here. Okay, so that's the end of sections 7.1, 7.2, 7.3. We did this in about an hour and 20 minutes, which is what normally happens in an in-person class. So perfect timing here, and then send me the magic word of this video for this unit.